Now I'm going to be talking about structured adaptive meshing, which was basically based upon what they call the block-structured local refinement based on the Berger and Oliger paper. What you have is a discretization which can be typically these techniques were evolved for finite volume discretization, and these techniques allowed you to have resolution where you needed within the finite resolution. So the refined regions get organized into logically rectangular patches, and you can have refinement in time as well as space. When you do refinement in time, it's subcycling. Not all codes that make use of structured AMR use subcycling, but it can be a very effective technique when you do put it to use. So why would you use AMR and when? You want to use AMR when you have a problem with a lot of skills and not enough resources to resolve all of those skills as needed at uniform resolution everywhere. So in that sense, what structured AMR does is it provides you with a way of compressing your memory as well as computation time usage. And when you don't have those requirements, you should just go with the uniform grid. For example, if your grid is refining everywhere, you have too many structures all over the place, and you need resolution of all scales everywhere in the domain, then AMR is no longer a useful technique, because then it's not providing you with any compression and it gets overheads. But even when these conditions are met, when you do have multi-scale problem, when you have structures localized within the domain, you cannot always use AMR, because what happens is when your overhead costs are exceeding the gain you have from compression, you shouldn't be using them. But more importantly, sometimes what happens is you're working with a higher order method and you encounter a fine coarse boundary and your solution does not match up to that higher order method. And if you really need a higher order solution, then you should not be using AMR techniques again. The flip side of using AMR, of course, is that you have a lot more complexity than you would with a uniform grid discretization, because you need a lot of machinery. You need interpolation to go from coarse to fine. You need coarsening. You need flux corrections, because at the fine coarse boundaries, you need to resolve your fluxes. And there are other resolutions that you need to do at fine coarse boundaries. So the machinery that you need in order to do the housekeeping for AMR is you need to maintain the relationship between the patches that are residing at the same level, within the level, and then you need the relationship between entities that reside at different levels, which means that you need for every fine level embedded within a coarse level, you need to know what are the connections between the patches sitting on those two levels. And then when you want to, the more difficulties come in when you're trying to parallelize it, because now you're distributing the information everywhere. And so you need to do the domain decomposition, and because you don't have simple nearest neighbor connectivity everywhere, what happens is that sometimes you have a trade-off between maintaining the proximity of the patches that need to communicate with each other versus the load balance, because you don't want to have some processes have too much work and some processes too little work. And in addition to that, depending upon how frequently you need to regrid, because this adaptive mesh refinement means that even with different levels, your grid doesn't stay stationary, it changes as the solution evolves. And every time, and when it changes with certain degree of frequency, you need to rearrange your grid, you need to regrid, and you need to redistribute. So, and this is when you're working with purely explicit solvers. This gets even more complicated when you have anything other than purely explicit solvers, because the bookkeeping gets more complicated, right? The basic abstraction that the structured AMR grids work with is that of a block. In this block, the green region is where what we call the active cells are, and the blue region is what are the halo of guard cells or ghost cells. The terminology varies from package to package. So the solution in this particular patch is getting updated on the green cells, which are dependent upon the values that are sitting in the green, because the stencil is typically going to go up, side, down, and so on. So this provides us a complete computational domain for an operator to work on, right? So you can apply the computational stencils on it. Now these halo cells may come from the same level in the mesh hierarchy, or they could come from the coarser level in the mesh hierarchy if this batch happens to be at the fine coarse boundary. If there is no subcycling, then the interface is simple, because all of these patches can get their halos filled simultaneously. So you have a single interface that says get guard cells, and every patch gets filled up with the appropriate guard cells coming from their neighbor in the same level or the level below. But if you have subcycling going on, the story gets a little bit more complicated, because now what happens is, in addition to filling these ghost cells from the coarser level, if your patch happens to be at a fine coarse boundary, now the next step within the subcycling, these need to be interpolated in time as well. And so either the application or the infrastructure can control where and when to fill them. Now, an important thing to note is that even though there are, this abstraction in most of the methods still holds true if you're using methods like multigrid. You still do the relaxation on a patch-by-patch basis. It's just that intermediate steps get more complicated. And then there are times when you move away from the semi-implicit methods, and Mark will talk about that when you interface with libraries that provide you with the solver's solutions to purely implicit solutions. So the approach is, you start with a UniGrid, which is a uniform grid all over the domain. And there are AMR packages that don't follow this, but vast majority of them, the patch-based ones, do. So you start with a UniGrid, and then you tag cells where you don't have enough resolutions, and then you try to perform a union on those cells to form rectangular patches as best as possible. And you can have embedded hierarchies within the mesh. Now, there are certain rules that are followed, in that a patch in the fine level needs to be completely embedded within the coarse level, and there needs to be some gap between the boundaries. You cannot have this boundary aligned with this boundary, because that gets numerically very difficult to resolve. So some of these constraints remain. And then these grids can be defined, dynamically created, and destroyed. So for building the hierarchy, what happens is, you fill the initial data at level 0, you estimate where the refinement is needed, you group cells into patches, and then repeat to the next level, and you maintain proper nesting. So in this situation, for example, here you have, this is where the structure is, and these are the patches that get tagged, but that by itself is not enough to provide you with a consistent grid. So some things around it also get built, which at a resolution, and then you have a hierarchy of mesh that gets built up, right? One of the parameters that you can apply to your refinement is the efficiency. And the trade-off is, when you apply lower efficiency, you have more refinement, more of the domains, the space getting refined into a level. And if you define a higher frequency, you really get your refinement very close to where your structures are. But the attendant complexity that comes in is that the process of regridding can become very much more expensive, because it's really trying to optimize, and it can take much longer time. So that's the trade-off that applications have to work with, and this is one of the parameters that applications can absolutely determine. And then there is the question of what happens when you're using adaptivity in time. So we have a fine spatial discretization, where the R is the ratio between the fine and the coarse grid. So what happens is, you advance the course grid. It goes from course time n to course time n plus 1. Now here the time steps are color coded depending upon the level of mesh that it's working on. So black is the coarsest grid. Then we have one time step advancing in the next level grid, which is represented by blue. And then we have the next time step going from T course to the subcycle time within the, well, that's not doing too well with my color coding. But the deep blue is supposed to represent the red. So this is the finest level. Now what happens is, for one time step taken by this level, there are two time steps taken by the finest level. At the time that they both arrive at the same time, there is a reconciliation that needs to happen so that things like fluxes and other components become consistent between the two levels. And this continues. So notice that now at this point in time, all of the mesh levels have arrived at the same time, and there is an overall global synchronization between all levels. So, and this is, so this kind of subcycling is applied recursively to all of the refinement levels. So these are the general structured AMR technologies, and now I will talk specifically about the two packages that are part of FastMath, Boxlib and Chombo. Both Boxlib and Chombo are multi-mixed language models in that they do C++ for all of their higher level data structures and all of their bookkeeping. And for the box abstraction that I had specified, the actual computations that go on typically are done in Fortran. Both the codes have reusable components. They have component-based design, and the components are basically taking the mathematical abstraction and mapping them straight away into classes. They both, the primary parallelization model is MPI, though both the codes support a hybrid mode now with OpenMP also. Chombo also uses HDF5 for I/O. And they both the codes have interoperability with Visit, PETC, Hyper, and so on. They are very similar at the lowest level because they had the same origin, but then the APIs diverged because of different needs, the different modes in which they were operating. Most of the examples from this point are from Chombo. So in Chombo, there is a general mechanism for distributing data. So here are the various patches, right? The various patches that are existing in the mesh hierarchy. So there is a class called level data, and I'll talk about that in a little bit, which defines data on a union of rectangles. So, and that is the meta information for the data here defined is kept in a class called box layout, which is a collection of boxes and their processor assignments. There is a special class within that is derived from box layout, which is called disjoint box layout. So box layout does not put any constraint on how the boxes can be. They can be overlapping boxes as well. Disjoint box layout insists that the boxes do not have any overlap with them at all. So disjoint box layout is what actually contains the data on which the computation is being taken. And you can imagine that when these disjoint boxes have their corresponding ghost cells around them, then they become qualified as box layout because now they're allowed to have overlaps. And the data is basically defined on these union of rectangles, right? And that class is called level data. Oh, okay, so this is what I was talking about, is that you have the disjoint box layout where all of the boxes are completely disjoint, and then they have their halo cells which are overlapping, and therefore and on the level data is the actual physical data defined on a box layout. Now, once we, and these are the other classes that actually do the operations on these data structures that are defined. So there is a class which does interpolation from coarse to fine. And so here what's happening is when you tagged cells for refinement purposes, and now they need to be populated when you created a finer patch, a new finer patch, and at that time, this class, the interpolation happens from the embedding coarse level into the embedded fine level, right? So this is the interpolation happens. Another time when this interpolation happens is when you are filling the ghost cells of a fine level, that is a patch on the fine level that is that does not have that's actually at a fine coarse boundary. The next class that is part of the bookkeeping operations is the coarse average class, and this is where you take data from the fine cells, you average it out and put it into the coarse cell, and this is when you're trying to do things like flux corrections or the synchronization after the time step has evaluated completely. Now here you see another data structure that's coming into being, and that's FRA box. An FRA box is a Fortran data structure for the data defined on a patch that is understood by Fortran. So when the control transfer overs to Fortran for the actual computation to happen, this is the data structure that understands both C++ and Fortran. So again, to summarize, the coarse fine interactions that happen is are at these boundaries where, so at these kinds of boundaries where, if you notice, this particular face of the box, the part of it is coming from the same level, part of it is coming from the coarser level, and so here the data exchange is going to happen. It's just an exchange copy over. Here there is going to be an interpolation involved. When you're doing the flux reconciliation, the flux reconciliation needs to apply to all of the dotted zones in these cells. The flux correction does not need to apply to the interfaces that are at the same level. Okay. We can go over this because this we have already talked about. The class that does the interpolation for filling up a patch is the piecewise linear class. But then this is the interesting one. This is the level flux register class, which ensures that the fluxes are all consistent at fine coarse boundaries. So the way the update is actually, if you have a finite volume discretization, the update is you compute the fluxes and at every cell, and then you add the fluxes taking into account the sign, and that gives you the new updated value. So what happens at the coarse level is that you simply compute the fluxes, you update your solution, and you're done. Things are much more complex at the finer level, because what happens is at the coarser level, the coarse level computes its fluxes, then it has to, if it happens to be at the same level, again it can proceed, but if it has a boundary with the fine coarse, then it has to remove the coarse fluxes, and it has to take the fluxes from the fine level, take the average of that flux from the fine level, and apply that to the coarse level. So effectively, what this is the operation. You take the change in flux, you subtract the ones calculated at at the coarse level, you add the one that's applied at the fine level, and then you update the solution, which means that the bookkeeping infrastructure has to know exactly where all of these interfaces are. So these are the various machineries for purely explicit solution using the AMR technologies. Now here let's go with an example of a heat equation on a single grid. So a heat equation solver on a single grid will look something like this. You have, if you wrote it in Fortran, you have a subroutine, and this is exactly how the calculations actually go on. Is these calculations go on in Fortran code. If you wanted to do this in C++, this is what the code would look like. You have a box that is defined. You have an FRA box which contains the solution data, and then you would do the iteration. But because we want to use the Fortran, we need to have an interface that moves from C++ to Fortran. Now, in Chombo, there is a very limited domain-specific language that actually carries out this translation. Because what happens is we want dimension-independent code, and when you have lots of arguments in a solver, it becomes a very error-prone process. And also, then you need to have a different interface for different dimension of the problem that you're working with. So what Chombo Fortran does is it manages this C++ Fortran interface, and it enables prototyping of the fast 2D code, and then it basically simplifies the code maintenance. And here is an example of what the typical translation looks like, is that on the C++ call site, before Chombo Fortran, this is how the interface would look. You had various arguments that then translated into, you had to make sure that you had one-to-one correspondence between these various arguments, that you had provided the right arguments in the right order, et cetera, et cetera. With Chombo Fortran, what happens is the C++ call site, it says is that there is all of these structures that I want translated into Chombo Fortran, and it does not specify the dimensionality, does not give any spatial extent of these arguments. It's the macros of Chombo Fortran that expand it appropriately, and it gets transferred to, it interfaces with the corresponding routines in Chombo, right? On the Fortran side. And so this is how the dimension-independent code can be written in Fortran now, is that instead of having to write arguments like this, where you're explicitly marking the do loops, the construct that, so this is what the macro will generate for you. When you're writing the code, what you do is you say CHF multi-do, and then you give the box, and you give the field variables that you're working with, and this will basically, Chombo Fortran will replace the indexing and looping macros appropriately depending upon the dimensionality of the problem. And at this point, I think I'll have Mark come and talk about the elliptic solver.
Yeah, okay. So this will be a vastly abbreviated introduction to the elliptic solvers, and it's going to be kind of influenced by things that I've been doing recently. So, but I'll talk just a little bit about how elliptic solvers work at a very high level, and talk a little bit about some recent work that I've been doing in getting Chombo, in utilizing PET-C's sparse solvers in general, usually algebraic multigrid, within Chombo. So you've been introduced to sort of the templating and the objects that you have for grid data structures in Chombo, for instance, these level datas and so on. And so you have a fairly straightforward class hierarchy in Chombo for operators, for linear operators, and for solvers and linear solvers. And so you'll define a solver, and you have a base solver class. It's linear solver that's templated on the type of data that you're working with. For instance, you've seen the level datas, which have these disjoint box layouts in them on these types of patches. And for a single grid solve, it's like this. And then for an AMR hierarchy, it's simply a vector of these single level operators. And then you define it, but you define your solver with giving it a linear operator and so on, information that's going to be able to need to solve the problem. And then finally, when you're ready to solve it, you have something where you're giving it the types it's been templated on for the left-hand side and the right-hand side. And so this is in the base class, so it's a pure virtual class. You can see here. So recently, I've been doing the last couple of years. I've been doing some work and doing matrix representations for Chombo, or for AMR hierarchies. And so so when you have these AMR hierarchies, they're very set up very well. They're very amenable to very optimal and fast solvers and geometric multigrid solvers. And that's what they've been using for a long time, and they're very effective most of the time. there are situations where applications that have very complex domains, geometric domains. They can either be boundary conditions or they can be internal material coefficient interfaces. And in situations like that, the geometric multigrid can be, theoretically, it can be made to work, but it's a much harder and takes a lot more of specific application tuning to make work. And it's algebraic multigrids, on the other hand, are very amenable to really anything that you're into a much broader class of problems, and they can deal with complex geometries and material coefficients very well. And so, so we've been doing things. So it's useful for some applications in trying to do some of this. But basically, we have some initial capability in Chombo to be able to create, well, we have two solvers, a level solver and an AMR hierarchy solver. And the AMR hierarchy solver is the one that I've been working on most recently, and it really just works about getting up. The only thing that's really hard about translating using PETC from Chombo is being able to get an explicit matrix representation of your operator on this hierarchy of grids. And so that's the interface that the new class provides. And then from there, you can create your own PETC solver from that. And so there's some ability to, you give it an operator, and it the new classes, the base class provides infrastructure for doing kind of the translations that are required in being able to take this AMR hierarchy. I guess we didn't have that other picture, did we? No. Okay. So, and it's set up so that the main thing that an application has to be able to provide is the raw stencil. So, for instance, the 5-point stencil, this is a dimensional independent, but you've seen many instances of the classic 3 or 5 or 7-point stencil for the Laplacian, and this is what the code looks like for writing the physics code would write just for the trivial 5-point stencil. But you can see of the definite Helmholtz problem in this case. So you've got an alpha plus beta delta squared, and so you see, and this is the way that you iterate in Chombo in a dimension-free way. You have these defines that are the number of spatial dimensions. You have these iterators that are side iterators, which are going just from one side to the other. So this is a way of iterating. It gives you the sign of it, and then you have these objects for cells, and you can shift them by the sign. So that now you can get your neighbor, and then you can put in a stencil value for this. This is basically just the -1 that you get in a 5 or 7-point stencil. And so this is just what a simple Laplacian stencil that you've seen many times. This is what it looks like in Chombo land. So that's probably as much as I think I'm going to go into to this part of the thing. This is a little bit of what it looks like to use this code in a simple way. You create a matrix, and then you create a PETC solver. So this is all generic PETC code here for constructing and solving a system, and then this is the part that I've added in being able to take a Chombo hierarchy of grids and an operator and turning it into a matrix and then throwing it over the wall to PETC. So that gives you a little bit of an idea of getting into the roots of the sort of the process that it takes to, which is a little bit interesting it's a little bit more technical, but you can actually see the process that it takes from going from these hierarchy of grids to a Chombo matrix. So what these AMR hierarchy methods, what they do is they have these hierarchies of grids that are overlapped. And so if you want a matrix, or there are methods that will do AMR that will flatten out that hierarchy and will have hanging nodes and so on. We don't use that kind of technique in Chombo or in Boxlib. But for a matrix, you have to flatten everything out. And so, the process that is involved in doing that is, or the approach that I've taken in looking at is, what I really need from the is just the raw physics or the raw stencil that you want to solve. And so the core thing that I need is really that 5-point stencil, that 4, negative, 4, -1, -1, -1 that you've seen 12 times in the last 24 hours is really the only thing that I really need from the user. And so the problem is that if I take that stencil, so let's just look at a really compact cartoon. This really isn't a valid grid, but a cartoon of an AMR hierarchy that I've squashed out and flattened out. So you've got 3 levels here: a coarse level, an intermediate level, and a fine level. And so if we just look at this cell right here and we just look at the classic 5-point stencil, I would get something from the user that would have the application that would have whatever physics they've got, whatever stencil they've got in space for wherever it is that they've non-constant coefficients and so on. But they don't have to know anything about boundary conditions. They don't have to know anything about what grid they're on, other than the delta H and things like that. But they don't know anything about what their coarse fine grid relationships are and so on. And so this 5-point stencil is all I really need, the only thing I really absolutely need from the application. And at that point, this is not useful as it is, because these stencil values refer to a few cells that don't exist in the matrix, because they're not valid cells where there's degrees of freedom, active degrees of freedom in the Chombo AMR hierarchy. So this is the cell that we're computing, so it's the center of the stencil. This cell here is in the Chombo hierarchy, but it's covered by a fine grid cell, so it's not a true active degree of freedom at the end of the day. And this is a real active cell, so this one's not a problem. This one is not on this cell. This reference here is a ghost cell on this middle level, but it's not a real cell in the problem, and therefore it's not going to be a cell in the PET-C matrix. And I should back up and say that I could put stuff like this in the PET-C matrix, and have relationships that sort of say that and put this cell in the PET-C matrix and solve for it all in one. But it's much easier to do it, to reduce out all of the ghost and fake degrees of freedom, and just give PET-C a matrix of only real degrees of freedom, because algebraic multigrid solvers are going to be much happier with that, for instance, because they don't have sort of funny interpolation equations in there. All of the equations look like the Laplacian, basically, if it's a Laplacian operator, obviously, that you started off with. And so you've got a cell here that's off the domain, and so the first transformation, you can do these transformations in any order, but the first transformation that I'll show here is I'll apply an operator, so I get something that I'll call A0, which is just this raw stencil. You could look at this as a matrix, as a wide, short matrix that has all of the ghost cells in the column space, but the row space is only the equations that are going to be the valid cells that are going to be in the system at the end of the day. And I want to compress out all of these fake column cells. So the first transformation is to get rid of this boundary cell. And so you have a basic transformation, some sort of an interpolation that says, what did I think? Do I think that this interpolant for this cell would be given the valid cells on the inside, and use that interpolant to essentially redistribute this -1 value into the interior of the domain. Then you apply, so you pick off, you basically are one by one getting rid of these fake cells. So the next one that I'll attack will be the coarse fine interface cells. So this cell here is hanging off here, and it's not a valid cell. So I'll use some sort of this is obviously just a cartoon. It's just looking at it's assumed there's only 2 interpolants here for this cell, which would be very poor interpolation. But you have some sort of an interpolant for how I'm going to how I would fill in this ghost cell given coarse grid data, and then use those interpolants to distribute this stencil value out to my coarse grid cells. So now I've taken this value, I've gotten rid of it, I've gotten rid of this guy, and I've added it into these valid cells in the mesh. And then finally, I've got a very simple one for the cells that are covered by fine grids, and these we generally use just averaging, and so it's very simple interpolation. And I take that cell and I distribute it in a straightforward way to the finer cells, and so at the end of the day, I now have a stencil for this one row of the matrix that does the right thing. That's some sort of a reasonable using reasonable interpolants for distributing the stencil out in a reasonable way to be able to have a valid stencil for the problem. And so it's really primarily a bookkeeping problem, and using interpolants that I can get from PETC or from Chombo for the way that they do these interpolants, and sort of grinding through and doing all these, and it's oblivious to the application. Now, the application sometimes will want to do some of these things themselves. For instance, so all of these operators that I've shown you are implemented as virtual classes or virtual methods in the class, and the only pure virtual method again is this get stencil thing that says give me your raw stencil. But some of these operators might want to be, the application might want to do something special and might want to do something. And so they're all virtual functions. And for instance, one of the applications that I work with does cut cells. And so they have very complex domains. And they, Anshu mentioned that when you have cut cells or you have boundary conditions in general, you generally lose an order of accuracy in that situation. And so the way that you can regain that regain that accuracy is to do a higher order stencil on the domain. So one application that I have, they care about they do a lot of work. Their whole application, or the primary thing that they're doing, at least in the mathematical side, is how to do these boundary conditions right. And so they care very much about how you apply this boundary condition operator. And so they do this in their stencil operator, and they add in a dummy class for a method for apply the boundary conditions that doesn't do anything, because they do that in their stencil operation, and that's all one big part of what they do. But they don't have anything special that they do for the coarse fine interfaces or for the fine grid interpolation. So they go ahead and use the built-in methods for that. But if somebody else had some very application-specific way that they wanted to do things, then they can go about and redo these methods, and the base class takes care of all the bookkeeping of the higher level stuff and assembling everything into a PETC matrix. And so right now this code is fairly specialized for Chombo and PETC. It's a fairly generic idea. It wouldn't be terribly difficult to apply this to say Boxlib, which has a very similar, as Anshu mentioned, a very similar data structures and approach to doing this at a high level, and another solver package like ePetra or something in the Trilinos library, or ML, that has a sparse matrix data structure, but we only work with PETC, or I only work with PETC and Chombo, so the current code is just hardwired for these two applications. And so this goes into a little bit of detail of sort of the nuts and bolts of how you go through this. I won't go into it, but this just gives you an example of this raw A0 matrix that I would get from the application. So this would be this A0. Semantically, it's not really done this way. I just go row by row, and you give me a stencil, which is a row of the stencil one by one. But if you looked at what I'm collecting over one patch, like a 2x2 patch, this is what this raw stencil would be. So this is a 9-point stencil, or I guess it's not. What is? I'm forgetting what this is now. But this is just a 2D Laplacian stencil. It gives you a little bit of an idea of specifically what these look like from an algebraic point of view. So I guess that is all of my extra slides.